This is a demonstration of the recently completed ALU Arithmetic Card. This card will join the completed Logic Card and upcoming Control Card to form the three cards of the computer's ALU. On the Arithmetic Card itself, we have the status LEDs down the front. The centre 8 LEDs show the 8-bit result of the addition, with bit 0 at the right and bit 7 at the left. At the far right is the carry-in LED, which is lit when the increment function is selected, and at the far left is the carry-out LED, which is lit when the result overflows. Moving further up the card, we have the arithmetic relays themselves. Each group of 4 makes up a single 4-bit adder unit, and each unit takes two single-bit inputs B and C, along with a carry-in bit, and each unit outputs a single-bit result, along with a carry-out bit. Each carry-in and out bit also has a negated equivalent, which simplifies the circuitry of each full adder unit to fit into just 4 double-pole double-toggle relays. There are 8 of these units hooked up in series, and that then forms the full 8-bit adder. Further up the board are the gating relays. The right-hand relays gate the result of the addition onto the data bus. The left-hand relays gate input C into the adder units so that when performing the increment B function, the C input is ignored. In the centre is the control relay, which sets the carry-in for the increment function and operates the output gating relays for both add and increment. Finally, at the top of the card are the connectors. Inputs B and C come in on the connector at the top left, and the result is placed on the databus connector next to it on the right. Next in line is the control connector, which provides the add and increment function signals. Finally, at the top right is the power connector, which supplies 12 volts DC. I'm reusing the same breadboard I used before when testing the logic card. To recap, there's a pair of dip switchers which set the B and C inputs, with bit 0 on the left on both, running through to bit 7 on the right. As before, the third smaller dip switch is unused for now. On the right hand side of the board is the 8 result LEDs, which are connected to the databus ribbon cable. These are the same 12 volt LEDs using the logic card, which have the integral resistor. Again, the reason for the mix of yellow and green LEDs was purely that I didn't have enough of either to go all one way or the other. Following the databus ribbon cable, we're back at the arithmetic card, and on from there is the test card. This time around I'm not using any of the buttons because I actually couldn't be bothered to wire out the links to the 20-way connector at the top right. Instead, I'm using a flying lead to tap either the add or increment lines on the power pin coming in from the right-hand ribbon cable. Likewise, power-wise, I've tapped the outgoing power ribbon cable on the left with some croc clips to power the breadboard. Following the power ribbon cable off to the right is a set of crocodile clips which then heads off to the power supply itself. This is the same Maplin 100 watt bench power supply used in my previous videos, and as usual it's set to the required 12 volts. I'll start with switching the power supply on, and currently with all switches on input B and C set off, all LEDs on the card are also off. I'll now run through all bits on input B one at a time, followed by the same on input C. This will test that all inputs are wired up correctly. Next, I'll set an on-off, on-off pattern on input B. And then run through all bits on input C one at a time, and this will show the addition operation on the alternate bits. To test a full addition to overflow, I'll set all bits on input C and then toggle the first bit on input B. Now, to get on with some actual addition. Setting input B to 7 and input C to 3, we get a result of 10 as expected. Another simple case is 10 plus 20, which unsurprisingly should result in 30. Finally, for an addition with overflow, we have 200 on input B and 104 on input C, resulting in 304. It's now time to test gating the result onto the data bus. Applying power to the add control line gates the result as expected. Changing input B to the on-off pattern again, we can try gating the result out. Switching to the increment function, we can add 1 to the result on input B and gate it onto the result bus. To test the input C gating relays, we set the last 4 bits of input C and then try the increment control line again. This will show the input C being disconnected, the carry-in bit being set, and the result being gated onto the data bus. So, that's it for the arithmetic card, all working as intended. The next card I'll be constructing will be the control card, which will produce the control signals for the logic and arithmetic cards, along with providing condition registers and zero detection. Together, all 3 cards will form the full ALU. Please visit my blog at relaycomputer.blogspot.co.uk to see more information on this arithmetic card and the ongoing construction of my relay computer.